All right, so hello everybody, I'm Dimitri, a PhD student in the computer lab supervised by Marcus Kuhn, and I'm here to talk about my work on electromagnetic eavesdropping of computer displays, and specifically about the DisplayPort interface. And just to get an idea of what we're talking about here, here's an example setup that we're using to make recordings for which you'll see the results later on. So on the far side of the room, you can see our target, which is a monitor and a laptop connected to it with a DisplayPort cable. And we've got a radio antenna pointed at it, and that antenna is going into the receiver that you can see in the other image, which is a software-defined radio and a laptop connected to it running our software to reconstruct the image. And well, it turns out that video cables, even though there are long wires that have rapidly changing voltages going over them, emit electromagnetic radiation, and that carries enough information for us to reconstruct at least a partial image being shown on the screen. We won't see every individual pixel, but we will see enough to, for example, be able to read text. And before we look at DisplayPort, let's just see what has been done before. So here's an example of what you might be able to do for an HDMI cable. Where essentially you take the signal coming from the cable, amplitude demodulate it, and essentially just reshape it into an image, and you will get a very noisy image with barely visible data. But because the signal is periodic, it's the same data going across every frame. You can take a lot of frames, average them all together, get the noise down, and get something that is, as you can see, perfectly readable. And other than HDMI, well, we essentially have 4 generations of video interfaces that might be interesting to an eavesdropper. The oldest ones, CRTs, have been targeted and demonstrated to be vulnerable to a similar approach back in the mid-1980s by a Dutch researcher called Wim van Eck, after whom this is also known as Van Eck phreaking. After that, we have two newer generations of digital interfaces, LVDS, which is the sort of thing that you might see, say, as an internal interface in a TV, which is basically just a simple serial interface carrying the information about the image. And after that, DVI and HDMI, which are fairly similar but have an additional encoding step. And for all of these, if you amplitude demodulate the signal, you can reconstruct the image. And well, nowadays we have a 4th generation of interfaces, which is DisplayPort. And that is a significantly more complicated protocol. And most important for us, it has a scrambler similar to what Gigabit Ethernet does that we'll go on about in a minute. And due to this, the existing attacks no longer work. And let's just take a quick look at what DisplayPort does. We have our image. It is split into 4 physical lanes, into 4 sub-images. And the most important part that happens after that is that the image data, instead of just being directly encoded and sent over the wire, is first XORed with a long pseudo-random sequence that we call a scrambler, similar, as I said, to what Ethernet does. And the reason this is done is it's not meant to be encryption. It's not meant to prevent attacks like this. It is meant to make the data look random for electromagnetic compatibility purposes, so that the signal energy is spread out across the spectrum, and we don't create a lot of noise in a very narrow slice if we have, say, a periodic image and interfere with other devices. But this also prevents the existing eavesdropping attacks from working, because we will just get random data back. And well, you might think, well, does this mean that we can just switch to DisplayPort and electromagnetic eavesdropping is no longer something that we need to worry about? And it turns out that the answer is, well, no. And here's a quick overview of how we attack this before we look at example results. So we've got our signal coming from the radio, and we want to do 2 things. First, we want to synchronize it with a local copy of the scrambling series. And we do that by saying, well, we know that there are regions of the image that are all zeros, blanking regions, there is padding in the data. And we correlate the input with the entire scrambling sequence to find some offsets at which it resets. We feed that into either a tracking loop or a mathematical model to get timing information for our local scrambler copy. And now we can use that and assume that the image shown on the screen has a certain set of colors. Say, if we're trying to eavesdrop on the presentation, we know that the background is probably white, the foreground is probably whatever the default text color is in PowerPoint. And we create template signals for each of the colors we're interested in and compute short-term correlations, essentially to see at every point in time, does the pixel currently going over the wire look like it's each of these colors, and assign the one that's most likely to the image. And now, even though the scrambler is not periodic with the period of one frame, the output of this is, and now we can do the same thing that we could with previous protocols. I average multiple frames together to improve the image. And well, here's an example of what we can do. Here's a test image that we displayed on our screen, a simple set of emoji with 16 colors. And this is what we can reconstruct. The vertical bars that you see here are a part of the protocol. They're just padding that's inserted by the DisplayPort protocol. And well, the edges between colors are a little bit fuzzy, but the image is still completely recognizable. And a probably more realistic scenario that you might be worried about is something like a presentation. And here is some text from a Google Slides presentation with the default settings. We didn't do anything to make this easier. And the output that we got from this. And this is a non-modified font. So this image actually contains more than 3 colors because the font is anti-alias. Essentially, the edges of all of the letters are blurred. But we can still get perfectly readable text because it shows up essentially as a negative in the background channel. And well, that's it for me. So if anybody has any questions, I'm happy to hear them.